The best way to do this is going to be to do it in the calculator and see if the calculator will show us what's happening. So let's make a list. I'm not going to write the list out. I'll just have you follow along with me. So if you get into your list, if you don't have L1 cleared out, let's clear it out. And I want you to put 1 in. Number 1, 1, 1. Put in 2 2s. Put in 3 3s. Put in 4 4s. Let's put in 3 5s. 2 6s. 2 7s. And an 8. 2 6s, 2 7s, and an 8. Okay. So what do I have? 1 1, 2 2s, 3 3s, 4 4s, 3 5s, 2 6s, 2 7s, and an 8. So if we graph that, that should look fairly normal. Let's play with the graph a little bit. Let's go to a histogram. Now, your previous person on the calculator may have these kind of goofed up and we'll do the same. So if plot 3 is on, let's turn it off and go ahead and turn on plot 1 for histogram. Or if any of the other plots are on, we need to turn them off. Otherwise you'll get an error. Somebody made this one green. Okay, and if I graph this and zoom 9 it, here's my graph. Now I don't really like it because the width of these bars is not 1. So I want to change that. So to do that, I'm going to go to Window, and you see how it says XSCL? It says 1.4, so it's grouping numbers together as 1.4. We want to change that to just 1. You can change the way a graph looks simply by changing your scaling. That's what that is, the X scale. And if I graph, now I have my 1, my 2, my 3, my 4, my 3, my 2, my 2, my 2, and my 1 for each of those numbers. Okay. Everybody with me? Now, what if I add 5 to every one of those inputs? Can anybody make a prediction what that's going to do to the graph? Is it going to make it taller, you think? Okay. Well, let's do that. Let's try it. So this will be something that you haven't done yet either. Let's go over to the top of L2. And if you press enter when you're at the top, it'll enter a workspace line here. So go ahead and enter into that workspace line. And we can add 1 or add 5 to these very simply if we just say L1 plus 5. And then press enter, and it should populate the list. It's magic. That's right. Magic. Okay. Now, we'll leave L1 there because we'll still play with that. Let's go back to our graph here. And let's turn on plot 2. And let's make sure it's histogram and L2. Sorry, I guess I could blow that up a little bit. Histogram and L2. And then if we hit graph, it's going to put 2 together. And I think we want to zoom 9 that again. And we'll probably want to change the scale as well. So if I change the scale, I'm going to go to Window. And I want to change that X scale to just 1, not 1.4. Okay, so a prediction that was made in this class was that the graph would get taller. Did it do that? No, it just is a shift. It slid it over to the right in this case. So let's take a quick note about that. Adding or subtracting a constant. Oh, sorry, let me zoom out so you can see all that. To a set of data is simply going to shift the data left or right. Or maybe graph. The important idea here is that the shape is unchanged. So the height didn't change, the width didn't change. Need a little Bob Dylan in our life. Okay? All right, let's try something else. Let's go ahead and go back to our list. Let's go up to L3. And let's try doubling our value. Do you think doubling L1, before you do it, what predictions might we make here? What do you think? You think it's going to get taller?
I would say so. Maybe that would make sense, I think.
Okay. I got a taller. Did I hear taller and wider? Or wider. Taller or wider. Thought?
My calculator does not have L3.
We'll fix that in just a minute. Okay. So, what I want to do then is I want to put in L1 and just times 2. Now, while I'm fixing that calculator, try graphing just L3. Okay. All right, so solved a couple problems there. Let's see what the graph looks like. I was just going to graph the 1. Yeah, it'd be real busy. So if I graph that, but then I change that scale to 1 again, what happens is we double values. But what happens if you double a 3? What kind of number do you get? You get a 6. If you double a 4, you get an 8. So whenever you double numbers, you always get even numbers. So the only place that these bars would exist would be where the even values are. So that's why there's a gap between them. So what changed? Did the height change? No, because the frequency is the height. We didn't change how many of those values we had. We just changed what their values were. So it did modify the width. Okay? Now, if you wanted to put these together, you could change the scaling to 2, and then if we graph it that way, each bar is a little wider, but the overall shape, what's the overall shape look like? The same. Yeah, the overall shape is the same, but it's wider. It did change the width. So multiplying or dividing will change the spread Remember, spread is your left-right. But the height and overall shape is still intact. It's unchanged. Oh, sorry. I'm pretty good at doing that. Feel free to, you know, I don't know, shoot me with a spit wad. No, let's not do that. That might turn into a war in this class. Okay. So transforming a data. We're going to learn more about transforming data a little later, but these are the basics. And the thing that I really want you to notice is that it doesn't really change the shape. Not much. It changes the width when we multiply or divide. If we divided, what would happen to the width? It'd shrink. Yeah, it'd be smaller. Multiply wider, divide shorter. Okay, moving on. The 68, 95, 99.7 rule, also known as the empirical rule. I don't know if I spelled empirical right. If not, blame an English teacher. This is actually a great shortcut. It's the kind of thing that actually the readers on the AP exam love it when you take shortcuts that are allowed, and this is a biggie. Okay? We know part of this already. If I take a normal curve, we know that the middle here is, what? X bar, your mean. Yeah, it's the mean. X bar, it's the mean. And if we go out one standard deviation in each direction, we find, yeah, we know that there's 68% of the data falls between these two. Right? 1 and -1. But what if I go out 2 standard deviations in each direction? Now, how to draw 2 standard deviations is the distance here is the same. Here and here is 1. So this is -2 and this would be 2. What we haven't learned is that 95% of all of the data in a normal curve falls between -2 and 2. So if I were looking at test scores, 95% of the test scores would fall between 2 and -2 standard deviations away from the norm. And if I go out all the way to 3 standard deviations, got any predictions? How much of the data falls between those two? 99.7, yeah. Almost all of it. Yeah, 99.7% of the data in any normal curve falls between 3 and -3. So to have a standard deviation value of greater than 3, that's really uncommon. In fact, greater than 2 is pretty uncommon. Yeah. I want to highlight a couple of other things, but I'll wait till everybody's sort of with me. Yes?
So does this empirical rule only apply to normal curves or just
It only applies to normal curves. Yeah, the 68, 99, 68, 95, 99.7 is only for normal. There is no such thing as a perfectly normal curve. Approximately normal is just fine. Roughly normal is even good. Yeah, okay? Remember, we're talking the science of approximations here, not the science of perfection. Right? We don't prove anything in this class. But yeah, no, it needs to be at least approximately normal or roughly normal. And usually we look for excuses to call things approximately normal or roughly normal, even when maybe they're not quite there. Okay. Just for the fun of it, you want to see what the class test score histogram looks like. This isn't this class. This is all classes. What would you say that the empirical rule would work for this? Yeah, it's approximately normal. Yeah, I think so. Okay. All right. Moving on to my next page here. I'm going to draw another normal curve, and there's some detail in here that I want you to be aware of with these empirical rule bits. So you've got your 68% here between 1 and -1. But how much do we have here and here? The curve is normal, so it's symmetric. So what percent must be in each tail? 16, that's right, because there's 32% left total. If you split that in half, you've got 16% in each tail. Now, we're going to see throughout the year that these are not exact values, but they are values that are close enough that you can use them and very quickly to answer questions sometimes when it's appropriate. So this is more like, I don't know, 15.93% or something. It's not exactly 16, and this isn't exactly 68, but it's close enough. And the AP loves it when we use it. So if I go 95% out, so I go out 2 standard deviations, how much is in each tail? That's correct, 2.5% in each tail. Okay. And the last one that we'll do, dealing with the empirical rule, I'm way out at 3 standard deviations here in each end, -3 and +3. So I got 99.7% inside. How much is in each tail? Almost 0, right? 0.15%. Or I think actually a better way to write that, to be honest with you, is 0.0015. It's not much. When you start talking about decimal point percents, I definitely think it's, my opinion is, the decimal's better. So again, the probability that somebody's that far out on any kind of situation where a normal curve applies is pretty slim. It's really slim. And this is true for any set of data that falls into any kind of approximately normal setting. All right. Any golfers in here? You think you, well, how many people have at least played golf, not miniature golf? Okay, so there are some golfers in here. All right. If you've played it at least once, you know the struggle. Okay. It is the most frustrating, worst sport I've ever played in my life, and for some reason I've played it more than once. I don't know why. Okay. Let's say there's a golfer, pro golfer. All of his drives follow a normal curve. Okay. The pro golfer has an average drive of 260 yards. Average drive. Okay? What is the probability that a drive chosen at random, or any particular drive for this golfer, is exactly 260 yards? How much? Yeah, what's the probability? So 50% of his drives go more than 260 yards, and 50% of his drives go less than 260 yards. What's the What's that? Zero. That's right. It approaches zero. The the probability of a shot, or drive, being exactly 260 yards is zero. Okay? So basically what's happening here is that a line, the line that we define the median by, is infinitesimally small. The line occupies no area under the curve. Oh. And that's about as calculus-y as this class ever gets. Okay? So for those of you that have had calculus and everything and go, oh yeah, that makes sense, maybe. Yeah, that's about the extent of where it goes for calculus for me. Okay? So here's why. Let's look at this probability table in terms of extremes, okay? Let's say you want to be 100% sure that something's going to happen. And on the positive side of this, the farthest I get out for z-scores is 3.49, and look how close to 1 that is. It's close, right? But if I went out 5 standard deviations away, or 10 standard deviations away, would I ever really get to 1? No, theoretically no. That just is kind of one of those deals where it just keeps getting closer and closer and closer and never gets there. For our purposes, though, and you can write this on there, if you have more than 3.49, we're going to say that that's 1. So anything greater, z is greater than 3.49, that equals 1. It's as close enough to a sure bet as it gets, okay? But in fact, it's still not entirely 1, but again, we're approximating here. Kind of getting back, it doesn't really correspond, but it kind of does, I think, at least in my own sick, twisted mind. If I flip to the other side of the page, my smallest z-score is negative 3.49, at least on this scale. And so anything, if z is less than 3.49, we're going to say that it equals 0 probability, because this is approaching 0. Okay? So if you're negative 4 standard deviations out, the probability that something is less than that is 0, is effectively 0. Okay? So the probability is, there is actually a probability there, but it's so small that we don't worry about it. It'd be such an incredibly rare thing. Now you will see times where you'll see really large and really small standard deviations. It happens. You'll see some problems, I'm sure, this year with that, but that's how we deal with that. So that's kind of I don't know, it's kind of like if you get way out there, your probability is 0, but the probability that you actually hit it exactly 260 yards and not 260 yards and 1/8 of an inch, right? Or 259 yards and 35 and 7/8 inches. Pretty slim, okay? It approaches 0. All right, one other idea. It's real quick and simple. Mean versus median. I know we've talked about this a lot, but I haven't introduced it in terms of like physics, I guess. Mean versus median. It's simple physics, don't worry about it. If I have a normal curve, the mean and the median should be in the same spot. X-bar and median, same thing. Okay, they should be at or incredibly near one another. But what if my shape isn't normal? And we've talked about this. So it's in balance, if you will. The X-bar is actually your fulcrum for like a balance. What if I drew a curve that had a skew right? Now, you guys did a great job on the test. Many people said that in a situation like this, we have a question kind of like this, that the mean is going to be greater than the median, okay? And that's totally true, but where is it? You can kind of identify it visually. Where do you think I would have to place this fulcrum triangle for it to balance? A little bit farther this way? Okay. How far? No? Back this way?
Right there.
Right there.
Yeah.
That's not
A
it?
little bit to the left.
To the left a little.
A little bit more to the left?
Yeah.
Right, I just drew it in. I didn't draw it in lightly. I think it's stuck there, okay? So what you're saying is the way it is right now, that this would tilt this way. Is that what you're saying? Okay, maybe so. Is it pretty close though?
Yeah.
All right. So this is your X-bar. It's the balance point. And you can kind of get a feel for it just with gut. Your gut can kind of tell you about where that balance point would be. Your median would be over here somewhere. It's going to be on this side of that balance point in this case. So the mean is where do we find the balance? The median is the actual middle value. Okay. If it's normal, the mean and the median should be the same or very, very close. Okay. All right. That's it. Good? Okay. Simple. Balance point. Fulcrum. Fulcrum.